All right, it's 1 minute after the hour, and we are quite lucky to have today's speaker, Dr. Sierra Ferguson of the Southwest Research Institute, who gave me a very nice summary bio statement here. So I think I'm just going to read it right now. So Dr. Sierra Ferguson is a postdoctoral researcher in the Department of Space Studies at the Southwest Research Institute in Boulder, Colorado. She studies the geology of the mid-sized moons of Saturn with this focus on the impact cratering history of the moons and how they can be used to assess the history and evolutionary pathways of ocean worlds in the outer solar system. Her research interests span the formation and evolution of icy/ocean worlds and developing missions to further explore those targets. She graduated with a Bachelor's of Science degree in Physics and Astronomy from Northern Arizona University and earned her PhD in Geosciences from Arizona State University School of Earth and Space Exploration in 2021. And with that, I will hand it over to Dr. Ferguson.
Thank you so much for the introduction, Pat. Let me get my slides up and running here and go in presenter mode. And I think you should be seeing just the regular slides, correct?
Yes. Yes.
Awesome. So like Pat said, today I will be speaking to you all about some of the work I've been doing on Saturn's moons. So this talk is titled Smashing Saturn, Insights from Impact Crater Analysis on Saturn Satellites. And I also, at the start, I'd like to thank my other co-authors on these various projects, Alyssa Roden, Michelle Kirchhoff, and Julian Salmon, who are all here with me at SWRI. And so just to start, I thought I would bring up sort of this big conundrum in the Saturn system, which is when and how did these moons form? So when I'm talking about the mid-sized icy moons of Saturn, I'm often talking about Mimas, Enceladus, Tethys, Dione, and Rhea. They're all relatively small in comparison to some of the moons of Jupiter, especially, but they also are extremely not, like, they don't make sense in the sense that they don't experience the same sort of crustal density gradient as you go out from Jupiter. So in the Jupiter system, you have Io, which has a super high silica content, pretty much no ice, then Europa, which has slightly less silicate, but more ice. And that sort of gradient continues out through Ganymede and Callisto. But with the Saturnian satellites, especially the inner ones, we don't have that nice sort of gradient density or density gradient. So Mimas is actually pretty high density, well, relatively high density. But then in the middle, you have Tethys, which has a density of less than 1. So it's less dense than water, which is its own conundrum. But the rest of them, they're not like the other satellite system. So the recent work from dynamical models has brought into question of when did they form. So some formation models place the ages of these moons between 4.5 billion years and 100 million years old. So this is quite a wide range of age estimates. Really, that just means, well, they could have formed anytime. So in trying to break down when did these moons form, we might think to go to Saturn's rings as the answer. And while the rings could help, their ages are also not well constrained. They also range between 4.5 billion years and 100 million years old. And so if the age of the rings was more well known, we might then be able to back out formation ages for the satellites due to some dynamical modeling. But unfortunately, the rings aren't going to be as much of help here. And so that really leaves us with one of the more tried and true methods of dating a planetary surface in planetary science, which is through the use of impact cratering. And so craters, or lack thereof on a surface, is a really tried and true methodology to look at surface ages. But if we don't know where the material creating these craters came from, a really meaningful age estimate actually kind of eludes us. So on the bottom of the slide, I show Enceladus, which has relatively few craters next to its neighboring moon Tethys, which is an extremely heavily cratered world. And so the main focus of this talk is going to be trying to look at what are these impactor sources that are making craters on these moons. And I'll get into a little bit more detail about this later. But what we're really looking at is what we call this planetocentric impactor size frequency distribution. So planetocentric is just this material that is orbiting around Saturn instead of the sun. And so this is more local debris to Saturn. But because it's local only to Saturn and is likely less stable than, say, heliocentric impactors like comets or other Kuiper Belt objects, it's actually quite difficult to predict what this planetocentric impactor population should look like at these moons. And so then backing out to the broader sense of the outer solar system, it sort of begs the question, is Saturn the outlier with this kind of funky cratering signature? And so previous cratering studies on Jupiter's moons, the Pluto-Charon system, and then some recent work on Uranus done by my co-author Michelle Kirchhoff have shown that these bodies in the solar system have all likely been impacted by a heliocentric source, and that's pretty similar. So this heliocentric source, again, just being sort of comets, KBOs that get brought into the inner region, into the outer solar system from farther out. And so, but then if you compare some of the crater counts from the Saturnian moons to, say, the Pluto-Charon data, which I've done with my data, it is not fully consistent with what we've seen on those moons. So this brings me to my sort of main motivating question for my work is what characteristics can we pull out from the crater populations on these mid-sized icy moons and actually be able to constrain the planetocentric population. And so for the purposes of this talk, I'll be focusing on Mimas, Tethys, and Dione. And so the Tethys and Dione results have been published, but Mimas results are sort of forthcoming. And so just for a little bit more background, just looking at the solar system as a whole, when we're talking about what's creating craters on these worlds, in the inner solar system, we're really so Mercury out to even Ceres, we're being cratered by asteroids and near-Earth asteroids. And thanks to return samples from the moon, we can actually date when these terrains may have formed. So we have the sample that was brought back from the moon to Earth, and then we were able to sort of correlate that age with a certain crater density on the surface. And so it's great with the moon, and then it's sort of extrapolated out to these other bodies. And then for the outer solar system, they are cratered by different materials. So this is comets, like primarily comets, KBOs, so Kuiper Belt objects, and sometimes debris orbiting the planet. So this is that planetocentric material. And the ages of these are not as well constrained. Because these impactor rates and impacting sources are different between the inner solar system and the outer solar system, we can't just as easily bring over the, say, lunar cratering rates and say, oh yes, because of the moon craters, the surface on Tethys is 2 billion years old. We can't quite do that. And so back at Saturn now, I think I've mentioned this already, but heliocentric, we're saying stuff coming from outside the system, again, Kuiper Belt objects, comets. And really when I'm looking at heliocentric cratering on these satellites, I'm looking at two scenarios from the Sonali et al. 2003 paper. This is one of these sort of foundational papers for outer solar system cratering. And so they present two sort of cases for the Saturnian system. So this first one is case A. So this is based off of counts on Jupiter's moons, Europa and Ganymede, as well as the present day sort of cometary impact flux rate at Jupiter. So this was looking at events like, say, like Shoemaker-Levy 9 impacting Jupiter and other sort of historical records of people thinking, hey, looks like something might have hit Jupiter. And then case B was then based off of crater counts on Neptune's moon Triton. And this then assumed a slightly different heliocentric comet flux. Now for a planetocentric material, this is where it gets a little funky. This is debris that originated within the system, and this debris is likely going to be sort of in the same orbital plane as the satellite. So we've got Saturn, and then that material is going to sort of likely be in that same plane. Now, some sources of this could come from material exchange within the system. Two of the moons, excuse me, have sort of moons of their own in their L4 and L5 Lagrange points. So these happen with Tethys and Dione. So Tethys has two co-orbitals, Telesto and Calypso, And then Dione's co-orbitals are Helene and Polydeuces. So those are just moons of the moons. And so theoretically, you could make an impact onto these sort of co-orbital moons and launch material off of them and re-hit and re-impact the sort of main satellite. And then we also have the issue of secondary and sesquenary cratering. And so when a crater is created on one of these worlds, it ejects off a bunch of material, and some of that material, if it doesn't reach escape velocity, can re-impact the surface, creating another crater. That's what we call secondary craters. Now, sesquenary craters, on the other hand, are still that sort of same ejected material, but it could have actually reached escape velocity, gone into orbit around another moon, hit another moon, or sort of stayed in the same orbit as the original moon. So while there are some ways to pick out secondary craters, which it's still extremely hard to do in the mapping of the Saturnian worlds, it's much more difficult to distinguish sesquenary cratering from primary cratering. And so my work sort of focuses on two lenses. So trying to unite sort of the surface geology with the sort of planetary dynamics perspective. So to do this, we're gonna catalog the global elliptical crater records on Mimas, Tethys, and Dione. And so these elliptical craters are really good for seeing if there is a preferred direction and impact, because these elliptical craters are created with really slow and shallow impacts. So it's not just coming straight down and creating a circle, it's coming out, or sorry, coming low. So materials sort of being excavated out to the side, so that you can actually kind of see the direction of impact from the thing that made the crater. And so if there's a pattern in these orientations of these elliptical craters, this could show us some preferred directions of impacting material onto the surface. And so we could then potentially use this orientation data to then sort of trace back to the other dynamical characteristics of the impacting population. And then sort of looking at the physical, which is more of the geology. And this involves completing crater counts of these regional areas on Mimas, Tethys, and Dione. So we're built for adding on to the size frequency distribution and the crater record that previous work has nicely done as well. So we're adding on to those counts. And what this does is it also helps us characterize the small scale size frequency distribution of material in this system, which is useful for saying, well, is there a large signature of secondary craters? Like, really just kind of trying to take a look at where some of this material came from. So you might be asking yourselves, why Tethys and Dione? There's a lot of moons in the system. Why these ones? So for Tethys, initially when I started this project, we weren't looking at Mimas yet. And so Tethys had better image coverage than Mimas. Tethys also just seems like a fairly ancient world that hasn't had a lot of active resurfacing like its neighboring moon Enceladus has. And so we've figured that Tethys likely has a pretty well-preserved crater record due to its relative inactivity. And there's also very few geologic sort of units on the surface, like there's different units within the Odysseus Basin and the Canyon system. But on the whole, it's really looking at variations in crater terrain, which is kind of nice in that we don't have to worry too much about different resurfacing mechanisms on different parts of the moon. Now for Dione, we also had similarly really good image coverage, also similarly sized to Tethys, which I found interesting from a sort of dynamics perspective of these two neighboring moons. If we saw one signature on Tethys but not Dione, that seemed like it would be a pretty good pointing way to point out, well, maybe like size couldn't have affected it. Maybe it was something else. Now Dione, on the other hand, might have had some more sort of geologically recent activity. So this is sort of best exhibited by the bright sort of scarps here on Dione, with what have been known as the wispy terrain. And so this may have been more recent activity on Dione, and thus if we look at the craters on there, then that could potentially also give us a window into a slightly later period in Dione's geologic past. And so that kind of goes along with this next bullet point of there being just more distinct geologic units. So we can start to look at a little bit more stratigraphy with these crater counts and elliptical craters on Dione. And both of these moons, from some thermo-orbital modeling that Mark Naveau and Alyssa Roden did, had shown that both Tethys and Dione could be either old or young. And their model pretty much always would get in a primordial Rhea. Mimas, they kept getting as a younger moon, but Tethys and Dione really could have formed at any point in their in history within their models and still evolved to the orbit that we know today. And then why Mimas? Mimas is a pretty small moon and just at first glance appears to be a heavily cratered world without much going on. And so, like I mentioned, this is the innermost major moon of Saturn, but some results from the Cassini mission and then later analysis of the tidal heating of these moons has suggested that Mimas itself might actually be able to also host an ocean. So libration data from Cassini pointed towards either an ocean or a non sort of equilibrium core. So it's like this would be a really sort of fluffy core, and it's not going to be perfectly spherical. It's just a funky core, but it's either an ocean or that. So this really was a kind of surprise, because when we looked at the other two really confirmed ocean worlds in our solar system, so one being Europa and the other being Enceladus, Mimas looks nothing like Europa or Enceladus. Europa A is much bigger than Mimas, but has a very resurfaced geologic record, full of tectonics, very few impact craters. And similarly with Enceladus, you have a lot of tectonic activity. Still, you actually do have some more impact craters on Enceladus, but it's still really limited. And so this really brings up this question of, if Mimas does have an ocean, why does it not look like Enceladus? And then to a lesser extent, why doesn't it look like Europa? But with Mimas, its age is also still sort of unknown. Could it be primordial? Is it new? Like, did it form out of Saturn's rings and migrate to its current orbit? Is its age somewhere in between, like going through a midlife crisis? Mimas itself is pretty enigmatic. And so we are going to be using the cratering record on Mimas to try and determine the ages, but excuse me, this age determination is really kind of hindered unless we can characterize this planetocentric population fully. And so this sort of obligatory method slide, all of the mapping that I'll be presenting, I've done in ArcGIS. And so for the elliptical crater mapping, I mapped across all longitudes spanning from 60 degrees south to 60 degrees north, so wide rectangle of the surface. And in the case of Mimas, I was actually able to map up from 60 south all the way up to Mimas's North Pole, because later Cassini passes did have some nice imagery of the North Pole. And then for the regional scale crater counting, I used more targeted images from the Cassini imaging system. And so for the elliptical craters, we started with the base map and then used supplemental Cassini imagery to sort of just verify crater shapes and just make sure we were identifying things the way that they should be. And so this figure on the right is just an example of what the mapping view kind of looks like. So on Mimas, like if your map projection was simple cylindrical, these craters would appear elliptical. But when you reproject that area into a south polar view, they don't appear nearly as elliptical. So this is just to show that we did take into account map projections when mapping these craters as well. And so, like that bullet point says, we reprojected where necessary so that we could try and avoid any shape distortions due to map projection. And then finally, the crater statistics we've done follow the pretty standard methodology, and we also use some new kernel density estimator calculations from Stuart Robbins. And so now getting into the elliptical craters first. This is the image on the right is an example elliptical crater on Mars. So these, like I mentioned earlier, are craters formed by a low velocity and oblique impact onto the surface. So this is an impacting angle of around 15 degrees or less. And what we determine as an elliptical crater is a crater such that one of the axes is elongated. So such that this ratio between the major axis and the minor axis is 1.2 or greater. I've seen some lower limits in the literature, but we went with 1.2 just to make sure that the craters we were including were more likely than not actually elliptical in origin and didn't deviate from a circular shape just due to, say, like crater rim modification or any other post-impact modification. And so what's been really great with these craters is they can record the direction of impact onto the surface. There's been quite a few studies in the inner solar system using these elliptical craters to take a look at changes in impacting populations over time, or even this paper by Sam Hollow in 2018, where they try to use elliptical craters on Mars to back out change it, like sort of estimate when Mars's obliquity had changed. So these are actually pretty useful craters to include in any kind of study. So we started to include them in the Saturn system. So this image on the left here shows the crater Penelope on Tethys. So this is just an example of how I would map this crater. So the ellipse is drawn around the crater, then the major axis is drawn, as well as the minor axis. And from there, my program will also calculate the crater azimuth. So that takes the angle measurement going from 0 degrees north going clockwise. And so for a crater like Penelope, this actually would record an azimuth close to about, I'd say, between 0 and 1 degree. So it's a very north-south oriented elliptical crater. And so then this Rose diagram on the right is an example of a diagram that I'll be showing later on as well. So normally this diagram will include multiple, like it'll include many crater measurements in it, but just for this example, this is what it would look like with Penelope's signal. So basically the direction of those bends is what is analogous for the crater orientation direction. And then just reiterating what our criteria was for being in an elliptical crater. So here's some of the results from the work I did on Tethys. So for Tethys, we counted over 1,000 craters that were mapped as elliptical. So based on this map, this is all of the blue craters. And then, oops, there is a typo on the bottom. This should be the Odysseus Basin, not Herschel. So this is the 400-kilometer Odysseus Basin on Tethys. And so we really did find a lot of elliptical craters all over Tethys surface. Some of it, like there are some areas where we didn't find any craters, and that's sort of gridding, and that could just be due to the image coverage. But these craters were fairly numerous across the surface. Now on Mimas, we still do see some elliptical craters, but it's far fewer in number than the other satellites. So this pink outline here now is the Herschel Basin on Mimas, and then the orange is illustrating the elliptical craters that we did map, and that ended up being around, I'd say, like 139 craters instead of the like about 1,000 on Tethys. So for sort of a global look, what was actually really interesting to me is on Tethys and Ione, really between about 30 south and 30 degrees north, we saw a pretty high concentration of east-west oriented elliptical craters. So for Tethys, this is the light purple on this figure, and then on Dione, it's the sort of light green lines here. And so these lines are literally just showing direction. They're not scaled to crater diameter, but it shows a pretty strong east-west signal on both Tethys and Dione. Now, when we got to Mimas, we still kind of saw an east-west signal, so that's with this sort of golden yellow color. But we also started to see more north-south oriented craters included in the mid-latitudes. And then by the time we got towards more polar latitudes, the north-south crater oriented elliptical craters really started to stand out far more. And so when we looked at these sort of rose diagrams for all three moons, again, Tethys Dione, that strong sort of preference for an east-west signal is still there, which is great. Love to see it. But then on Mimas, this east-west signal is there, but the north-south signal is pretty much there, but as well, but it's also stronger. So this was actually kind of unexpected for us, just because what we had seen on the other two satellites was that the east-west craters were the predominant signal, with then craters oriented just isotropically around every other orientation. But the fact that we had an east-west signal along with the strong north-south was actually pretty unexpected for us. And so then with the Tethys data, we also took a look at if there were any relations to sort of stratigraphic relationships based on some other unit definitions. So this is a map for Tethys. So we have just the Odysseus unit, the light cratered plains, fractured crater plains, and this is just over the Ithaca Chasma canyon system. And then the smooth crater plains, and the coral background color is the dense crater plains unit. So on the whole, most of our elliptical craters fall in this dense crater plains unit and are still oriented east-west with a signal, isotropic signal around all other orientations. And then sort of going up in the Stefan et al.'s sort of stratigraphic relationships, we start to see this east-west signal is even stronger with less of an isotropic signal. And then up to the fractured crater plains, it becomes a little bit less structured with the east-west orientation, and even more so as we get to these younger units too. Like they still have some degree of east-west trending, but they also have other crater orientations as well. And so we did a similar analysis based on unit boundaries defined by Michelle Kirchhoff and Paul Shank's work on Dione, and their densely crater terrains units 1 and 2 are actually a small fraction of the surface area for my mapped areas, and so that's why their numbers are low. So n equals 3 and n equals 35. But then these sort of middle units, the smooth terrain, faulted terrain, and the intermediately crater terrain, all have pretty strong east-west signatures, with again a little bit of that north-south, but still this east-west orientation is pretty dominant. And then with these younger units on Dione, again, we had a very small number of them, partially because of just the surface area was much smaller, so the chances of finding these elliptical craters in that area were far lower. And so now looking at a histogram of these distributions on Mimas, we do still see that like small east-west peak, but this north-south orientation peaks as well. And so this is just showing all of the craters sort of between 25 south and north, and then all of the craters above 25 north and below 25 south. So this is about sort of that mid-latitude area in which we found the east-west signal was the most prominent. And then looking at that on Tethys and Dione, we see evidence for that sort of background level isotropic population of elliptical craters, but then this east-west signal really still does pop out of the data. Now, I do want to point out that the y-axes on all of these histograms are slightly different from one another because Tethys and Dione had far more elliptical craters. But if we scale the Mimas data down to say Tethys, the Mimas data would just sort of be within the noise of what we see on Tethys. So like we're seeing a signal for Mimas, but if this was on another moon, we might not even really notice it. And so because we noticed that these higher latitude areas were more, at least on Tethys and Dione, were sort of more isotropically oriented with elliptical craters, we thought, well, if in this area where isotropic elliptical craters are dominant, how well do our outer solar system production functions work with determining an age there? And so to sort of test this out, I mapped an area on Tethys near it, in and around Ithaca Chasma. So this spanned a latitude of 30 north to 60 north. And then on the right, we had the the cumulative size frequency distribution for that crater count. And what that came out with was an age of 4.4 billion years, plus or minus 100 million years. And so this blue line is representative of that case B scenario. And so this is the one that was based off of the data at Neptune's moon Triton. And so while this does give us an age, and that's awesome to see, and the fit to our data actually isn't that bad, this age is dependent on uncertainties in the source population. So not all sources are incorporated. This is a primarily heliocentric impacting flux. So effects of secondaries or sesquinaries aren't really in this. And kind of the elephant in the room here is we haven't made absolute age measurements on AC material yet, which would be incredible to have, but we just haven't done it yet. And also the age of Triton's surface itself is also uncertain, because Triton might be a world that has been actively resurfacing and may have erased some of its craters. So there's still also a debate of how old is Triton's surface. And so kind of just to summarize the elliptical crater work so far. So these characteristics on Tethys and Dione, we see a strong signal of east-west trending craters. And so we need a source or process that can explain this for both moons in a similar longitude band. And so to me, looking at some of the stratigraphy, this kind of seems like maybe there was a sort of spike in elliptical crater formation, so that maybe there was this material that was available to create elliptical craters, but there is potentially a pulse that just made it more likely to get east-west orientated craters. Now, to explain the isotropic ones, we would still need a crater at the surface evenly from 60 north to 60 south. Has to be a common process at both moons. And then the source or process would still be sort of agnostic to the impactor direction. And so through the mapping that we've done and more mapping that we want to do, we can start to build additional constraints on the dynamics of the source population, and better figure out what the bombardment environment at Saturn looks like. And so on Mimas, again, we still need a process that can create the east-west signature in a similar longitude band as Tethys and Dione, but just still explain that we're getting craters at a much lower rate. And so this could potentially be saying we're getting a decrease in material with time, because maybe this started at Tethys and Dione and then just moved inwards towards Saturn. But then the north-south oriented craters also present kind of a conundrum. Like these, we would still need to make a pulse material that orients craters in that direction. Maybe this is a shift in material source, or maybe, and there is a small isotropic signature, but it's really not as prominent as what we've seen on Tethys and Dione. So this gets to our question of where did the elliptical crater material in Mimas come from, rather than the sort of isotropic signature that we've seen on Tethys and Dione. We see both a north-south signal and an east-west signal. So this really does differ from Tethys and Dione. So one thing that we're testing is whether or not this could be, the elliptical crater orientations could be made as a result of sort of a flattening debris disk. So as this figure from Brahek in 1977 shows, as you have a disk, this could be very much dispersed, but then this disk could flatten out. And maybe, just maybe, that flattening of craters could explain that east-west signature, while this isotropic signature could be explained by the more sort of dispersed disk. Now, we don't know if that's for sure yet. That's something we're still testing. And so are these craters useful for constraining the ages? I would say yes. But now, is there a global pattern? There is a global pattern here, with crater orientations being much more prominently oriented in an east-west direction in the mid-latitudes, alongside an isotropic global signature on Tethys and Dione. And we do see this similar signal on Mimas, but it's far less prominent. And Mimas also displays an equally strong north-south crater orientation, which again, far did not expect that. And so if they're going to this question, if there was a signal, can we use this to separate out the likely impactor source? And we think we can. Our regional mapping on Tethys does suggest that there's a similarity to the Triton SFD. So maybe this is planetocentric material as well as sort of satellite centric, but that's still an area of ongoing study. So now we're going to get into the regional cratering study. So this is a map from my 2020 paper where we looked at the crater distributions of these 5 areas on Tethys. So started with one near sort of near the Odysseus Basin, 2 sort of near Ithaca Chasma, 1 right on Ithaca Chasma, and then region 4 was meant to be to try and get close to Odysseus's antipode, because on places like the Moon and Mercury, we've seen some weird sort of terrain, sort of antipodal to large basins on those bodies. So I thought, well, let's check for any kind of antipodal weirdness on Tethys. And spoiler alert, there really wasn't as much antipodal weirdness. But before I start to show some of the crater distributions, I do want to just give a brief reminder of how these size frequency distributions work. I know they come up a lot in planetary science, and they're not always the most easy plots to understand, but these curves allow us to really link between the craters themselves and the impacting populations. So on the y-axis, we have the crater density. So this is in normalized per unit area. And then we have the diameter of the craters. And so on the left here, we have a model, very much cartoon size frequency distribution. And then on the right, we have sort of an example planetary surface. So for this planetary surface, it has very few craters. So it's going to have a pretty small SFD. Now, if we add more craters to the surface, it sort of brings this plot up, and it changes the size frequency distribution. So if I was looking at relative age relationships between surface A and surface B, I would say that the first surface is younger, there's fewer craters, it has a lower crater density. And then this surface B is the older surface because there's more craters. So it's been exposed to space longer. And then what we can also do is add in a production function. Excuse me, so this is the black dashed line. And this is a way that we can sort of take the cratering rate that is expected for certain bodies in the solar system, and then extrapolate that to the actual crater distributions that we see. And so this production function and the work that I've been talking about already is analogous to that Zonley et al. Case A and case B. And so from a lot of the mapping that we did for Tethys, we have these size frequency distributions for all 5 areas. So for anything in the blue color is case B, the dash sort of magenta color is case A. And so when we look at crater diameters around 5 kilometers and larger, we do see a pretty good fit with this case B scenario, which is awesome. But we still deviate off of it a little bit in region 5, and that's the one on Ithaca Chasma, but it's still within the error bars, so it's still fitting. But then when we look at case A, we do see a fit at smaller crater diameters, so say like 1.5 kilometers ish to about 5. But interestingly enough, region 3, it doesn't fit. And even if I fit the curve so that it does go up here, we still significantly overshoot the distribution at the higher end. So this to me was saying that, well, neither of the currently predicted production functions fully fit with the craters observed on Tethys. So to me, this was more indicative that there is a more dominant planetocentric source creating the craters here on Tethys. So then we decided to move on to Dione. So Dione, again, much more tectonically modified, also a candidate ocean world. And so we looked at these 4 regions on Dione. And I should also correct this to say that This paper did come out earlier this year in JGR Planet. So if you're interested in Dione, highly encourage you to check that out. And so we did a similar comparison to the Zonley et al. Functions. And again, case B is fitting pretty well at larger crater diameters. So region 1, we get a good fit, once again, from 5 kilometers up to about 20-ish. Then there's a weird sort of change in slope at about 25 to 30. That's still kind of puzzling. Region 2 really only matches nice super well at a much smaller range. Similarly with regions 3, but region 4 still matches those higher crater diameters fairly well. But now case A will again still is matching these smaller crater terrains, or sorry, smaller crater diameters, but neither one perfectly fits. And so if we try to fit the case A lines to the larger crater diameter, so shifting it down to match this, then we're vastly under predicting the amount of small craters that should be on the surface, and which we know are on the surface from the mapping. So again, there kind of has to be another source that is making these craters that's different than what we're seeing on the other bodies in the outer solar system. And so now going on to the more recent work I've been doing on Mimas, we mapped across the North Polar terrain of Mimas, some trailing hemisphere areas, as well as some detailed mapping of the Herschel Basin and in and around Herschel. So we looked at the interior of Herschel, its ejecta blanket, as well as up to a full basin radii out from Herschel, just to look for differences in the cratering distributions. So really with the Mimas mapping, we also want to take a look at this relative age of Herschel. Because this is such a large basin and is the biggest feature on Mimas, it's really an anchor point in Mimas's history. So we want to get an idea of how old is it really, and are we sure it's not a planet-killing laser? It's not a planet-killing laser like the Death Star. I can say that right away. But we really want to get the sense of when could Herschel feasibly have formed, because the size of impactor that you need to make Herschel is much rarer in the solar system to come around, have a big enough object be able to create this large basin, and also create this large basin without destroying the satellite. And so some of our early results with the Herschel Basin mapping do suggest a sort of younger Herschel. And so our older regions, so the North Polar and the trailing hemisphere, as well as the full crater radii away from Herschel, all reach what we call crater saturation. And so this is where new craters are being made on the surface, but they're sort of erasing other craters. So the surface is sort of saturated in the sense that the crater distribution really isn't going to change much over time at that point. Whoops, sorry. And what was really nice to see and sort of reaffirm a good sort of sanity check on the mapping that I was doing was that the Herschel interior and the Herschel ejecta blanket both have relatively lower crater densities. This is good because these are things that would have been cratered after Herschel was formed. So theoretically would have been exposed to space for not nearly as long as some of these other areas on the moon. And so I did a first order sort of calculation at how thick the ejecta blanket could be. And so because I wanted to see, well, at what diameter of crater on the ejecta blanket are we actually going to be recording new craters and not just craters that were there before the blanket was in place. And so this came out to about 13.5 kilometers. So any crater that was 13.5 kilometers or smaller, likely to the first order, would have been buried by the Herschel ejecta blanket being in place. And so based on our SFD, the largest crater that we see in the ejecta blanket here is at about 10 kilometers. So to me, this says, yes, we are recording what is likely just the more recent impactor flux on this ejecta blanket. Now, when we compare the results I've gotten from Mimas to the results on Tethys and Dione, there are similarities. So for this plot on the left, this is MIMUS data scaled to Tethys gravity. So we do see pretty similarly sloped distributions for craters from about 2.5 kilometers all the way up to about 15-ish kilometers, but then we got a little bit of a break off of change in slope at the higher diameters, which isn't as surprising to me. But the Herschel Basin, this yellow line, really does stand out far out as the example of a really low crater density surface. Now on Dione, there's a couple similarities in slope here and a little bit here, but the Dione higher crater diameters do just have different slopes. It was, again, kind of surprising to see that, but their slopes do differ, and especially as we get out to higher, even larger diameters. So there are some similarities. So to me, this is saying, well, MIMUS likely still is being cratered by a predominantly planetocentric population. But this really gets at this question of MIMUS's surface geology and its cratering history is actually more complex than some people might have initially given it credit for. And it really does require a merging of a geologic and dynamic perspective. And so why do we observe this north-south elliptical crater orientation on MIMUS, but not Tethys and Dione? And if this elliptical crater population on all these moons is formed by a debris disk, say at Tethys and Dione, maybe that disk just didn't reach MIMUS. Maybe MIMUS's low gravity is maybe more prohibitive to capturing material that can make these elliptical craters. Or maybe MIMUS really is just a younger satellite, and it just kind of missed that pulse of material that was responsible for the cratering on Tethys and Dione. And so this then sort of begs the question, did MIMUS receive less material overall, or did it just receive less of the elliptical crater forming material? And I'm more inclined to say that it just received less of the elliptical crater forming material, because when we look at the other crater distributions, they're similar enough in density that to the other moons that's, to me, says, well, seems like they received a almost equal amount of material. And so with Tethys and Dione, we see this planetocentric cratering is dominant on the surface, with maybe some hints of heliocentric. Excuse me, there are regional differences in the Tethys data sets, mostly at the small crater diameter, so around 1.5 to about 5 kilometers. And Tethys still, to me, is sort of the best example, one of the more classic examples of relatively old and unmodified surface. Dione's small crater populations don't seem to be enhanced like Tethys is, and Dione's small craters seem to have been more erased due to some kind of resurfacing process on the satellite. And on Dione, their mapped areas are likely similar enough to one another in age. But both satellites do show evidence for a unique planetocentric source, and this has yet to really fully be characterized. And then at the larger diameters, so around 10 kilometers and higher, the slopes of these SFDs match the currently predicted production functions at Triton. So while the source of the material is likely different, there are similarities in their size distribution. So that's kind of a puzzling link between Saturn and Neptune even. And so looking at these impactors, again, through the lens of the crater counts, this Saturn-specific planetocentric population is pretty, in my view, pretty likely to be responsible for the majority of the cratering in this system. And these elliptical craters are unique in that they have this preferred orientation in the east-west at the mid-latitudes, and give some key information about the dynamics of the source at Tethys and Dione. Now, for the sort of physical side of things, these production functions seem, especially for small craters, seem to very much underestimate the amount of small crater material that would be available to create these small craters. So this would be about 100 to 500 meters in diameter for the impactor itself, not the crater. But we might just be underestimating the amount of material available to create those craters at Saturn. But at these larger diameters, the slopes of these SFDs do match the Triton functions pretty well. The source is likely different, but there are still similarities. So just as, again, some of the conclusions that we have so far is that the elliptical craters on Mimas and are oriented in both this north-south and east-west direction, which is very much in contrast to what we see on Tethys and Dione. We are working right now to evaluate a sort of debris disk origin for these elliptical craters, so stay tuned for that. And some of the preliminary mapping we've done with the Herschel Basin and the trailing hemisphere do display some similar size frequency distributions to Tethys, but they are still different. They are still different at the smaller scale. And so this does imply a similar source origin for these craters. And we're still analyzing the relative ages for Herschel. So hopefully that will come out with the paper. Just to briefly mention, we are continuing this work on Rhea and Iapetus for the elliptical crater. So we're really then going to the outer edges of the Saturn system to see, is there even an elliptical crater signature there? If there is, that's sure going to be weird and we're going to have to explain it. But if not, it also will tell us a lot. And so just to summarize, just some future avenues of exploration, more dynamical modeling of mapping of secondaries and sesquiternaries on the Saturnian moons would really help us disentangle what was a primary cratering event versus a post-primary event, and also a more complete understanding of ages in the outer solar system would really be aided by a return to the Uranus system and the Neptune system. So thankfully, the most recent Planetary Science Decadal Survey heavily prioritized a Uranus orbiter and probe as the next flagship mission after a Mars sample return. So hopefully with the start of the Uranus orbiter and probe mission, we'll be able to go back to Uranus and get a more complete understanding of the crater history of these incredible satellites. And also Neptune and Triton, well, so really Triton may also be a system that has been heavily dominated by planetocentric cratering. So a return to the Neptune system will also be extremely valuable for constraining the impactor populations throughout the outer solar system. And with that, I'd like to thank you for your time and we'll happily take any questions. Thank you.
All right, let's thank Dr. Ferguson for an amazing talk. You can express your gratitude with the reactions or in the chat directly. I see a few applauses going up from the reactions. That's very nice. How we'd like to do this is you can type in questions in the chat if you like, or you can express your interest in asking a question in the chat, and then you can unmute and come in and ask your question directly. I'm going to give a second or two for someone to chime in. Do we have a request? Is that an applause or is that a hand?
I think it's an applause.
Well, it's a different kind of hand. How about a hand? Yeah. You know, I do have questions, but I wanted to let the audience at large ask. Let me bring up the chat here. Has anything appeared in the chat? No. Alan, would you like to ask your question directly, or shall I read it?
Oh, you can read it.
I'll do my best Alan Freeman impersonation. Actually, I don't have an Alan Freeman impersonation.
Hi there. That was really interesting talk. I'm just wondering, starting off with, is there a theoretical reason that these craters are elliptical rather than some more complex, more terms in it shape?
Yeah, that's a really good question. And from what I've been able to sort of gather from some ISAIL impact modeling that Gareth Collins and his group have done with these craters, is that the elliptical shape is almost just a byproduct of the focusing of the energy, I think, because as the impactor hits the surface, this energy sort of gets focused forward, and then the excavation pushes material out. So I think it's just more. It's like the more energy efficient way for the impactor to distribute the energy into the surface, but there could be a little bit more than that, but that's at least has been my understanding from some of the literature.
Thanks.
Is there another question from out there in chat land?
Well, I can ask another sort of a different flavor. That elliptical crater you showed on Mars, that very early on had like
Mhm.
two precursor, two craters on one side of it and sort of extension along to the other side.
Mhm.
Yeah, do you see any of those on these outer satellites?
I haven't yet. I think part of it is just because the image resolutions are so different on Mars versus what I've been using on Cassini. I mean, on Saturn from Cassini.
Mhm.
Like this, I believe this is either from CTX or Themis, which are in the like at least I think like meters per pixel level. So it's like 10. I think CTX, I'm not a Mars person, so I very well may be wrong, but I think CTX is more on like the tens of meters per pixel, and what I've been using on from Cassini is more on the hundreds of meters per pixel. So it very well could be there, but we just might not be able to see it yet. So like I would love to go back to Saturn with an even more nice camera and get some updated imagery there, because I think that would be really elucidating.
Cool, thanks.
All right, Sierra, I'm going to exploit my advantage as the LPI virtual seminar series co-chair to ask a question here. It's based on the north-south orientation of the of rift zones that there are these fracture zones that you see on satellites like I think in particular Dione and Rhea. They have these really interesting, they're like hemispheric in scale, and they have a north-south orientation. I'm going to try to keep the setup for this short, but on Pluto we see this terrain called the ridge trough terrain, which is also sort of like it's north-south. It's to the west of Sputnik Planitia. But for several reasons, based on mapping and modeling of stresses in icy shells and satellites, we think it was originally on the equator. So we have to figure out some true polar oneness scenario if we're getting it back onto the equator. If you do that, then you have a scenario for generating a north-south population from the same sort of disk that you had before. The problem being that the one planet that shows that is not the ones with the exciting tectonic systems, but it's Mimas, which is a blob tectonically. So I mean, it's what that means maybe is that you had the other satellites are just simply the surfaces are younger. But I wondered if you had any thoughts about how the cratering records may interact with movements of the planets with respect to their spin axis.
That's a really good question, Pat. And I think with Mimas, if there was some kind of true polar wander, like I personally don't think there was, at least with Mimas, we would still sort of rotate that east-west signal that we see now to still a north-south. So even if there was a rotation with Mimas, we would still have to explain the north-south somehow. But what I had looked at was if there is any relation between orientations and say like the predominant orientation of like Ithaca Chasma or some of the wispy terrain. And it just didn't seem to follow with any of those other tectonic features. I've been talking with Emily Martin at the Smithsonian about some of her fracture databases with my elliptical craters, and we were trying to see if there are similarities, and so far we haven't seen a lot of similar orientations between them. Like one thing I didn't get a chance to mention was with the regional cratering, I've looked also at polygonal craters, which are pretty nice in that they can help you see sort of some subsurface fracturing and take a look more at the general satellite-wide fracture history. But we haven't done a whole lot with those yet. But I think those crater morphologies would be even more useful for looking at the changes in sort of tectonic patterns on the satellites.
Are there many polygonal craters out there?
On Tethys, I found, I think, at least 40 to 50. Chloe Bedingfield has a really nice paper on polygonal cratering on Dione, and I think she found several hundred or so. Like her paper does a really nice job of looking at the sort of statistical distributions of these polygonal craters on Dione's surface. And I think she's also been seeing them on, I want to say, at least Miranda and a couple of the other Uranian satellites too. And so I think they're a really, really good crater morphology to use to take a look at the interactions between craters and other geologic processes.
All right, well, that's, there's clearly some references I need to follow up then. I've got a CDAP, which was resurrected after, the PI Paul Byrne moved institutions. I was very busy with the decadal survey, but we're gearing up to look at, true polar water type models for stress generation at the satellites, and maybe just maybe there may have been a different orientation, but the cratering records seem to show that the surfaces are pretty young.
Mhm. Yeah, and what like the approximate age we're getting for the older terrains on Mimas is around 1 billion years or so.
Mhm.
And to me that I'm more comfortable with that kind of age for Mimas instead of a several 100 million-year-old age
Oh,
for
okay.
Mimas.
Mhm.
Like
Yeah.
I am much more comfortable with that like with the billion years, because that gives you enough time to create the cratering signature that we see today. Like to me that feels like the more more comfortable age to give that surface.
Less arm waving.
Mhm.
I did have one more question with respect to these satellite systems. It's like on either side of Saturn, there seems to be a heliocentric population, and on Saturn, it's the one with the planetocentric. And I'm wondering, is there some trade-off curve going on there in terms of the orbital velocities and the masses of the satellites, or something about why Saturn's distance and why Saturn's, Saturn it falls into a notch between two different,
Mhm.
do you have some insight into that?
That's a really good question, and one that I don't fully have a good answer to, but I think it's really interesting in terms of what the sort of architecture of the satellite systems are, just because Saturn's the architecture of that system really doesn't look like any of the other giant planet satellite systems, and very much could be the ones we see today are more second generation, maybe our second generation moons, or maybe maybe there was another Titan-sized body that got disrupted, and maybe that could be responsible for a lot of that planetocentric material. Like there's just, I think Saturn it's great, but it's also confusing in the sense that it's kind of a dynamical playground of
Yeah, right. So
a lot of different things could have happened.
it could be stochastic rather, if you switch Jupiter and Saturn in place, your spatial pattern would just change because
Mhm.
it's just the systems are just different.
Mhm.
Yeah, okay.
Mhm.
All right, cool. Thanks. Anyone else? We'll give one more opportunity for questions. If not, let's thank our speaker again, and we'll see you at the next installation of the joint LPI at the LPI virtual seminar series.
Thank you so much for inviting me.